It's a great pleasure to be here, and I think I can describe in a few phrases his description of my interests. I'm a little bit like an oil slick, 100 miles wide and about a molecule thick, although in some areas maybe a couple of molecules thick. And I actually packed carefully to come on this trip, and then I had a moment of fear this morning in the cab from the hotel to here. I packed this shirt partially because it's kind of a nice summery shirt, but also I thought, well, orange, that's University of Miami has that color. And then in the cab I thought, oh my God, is that Florida State? Is that the University of Florida? Am I going to have to go back and put on a t-shirt or something? And then I saw the sign of the health center. I said, oh yeah, okay, fine, I'm all right. So I'm going to give a talk, not technical, or at least I hope it won't be, that it will be trying to show some things in this specific application of ranking and ensemble estimation, and I don't think I'll actually get to the and part, but we'll see. So part of it is the specific goal of ranking, and part of it is a little bit of an advertisement, if you'd like, for Bayesian thinking and Bayesian formulation. And that's very different from being a personal Bayesian, but to push the idea that the Bayesian formalism is extremely effective at, first of all, formulating what you'd like to do and then being able to do it, irrespective of whether you later want to make sure it has good frequentist properties, Bayesian properties, or whatever. It's just a nice conceptual framework, irrespective of your statistical philosophy. So let's not preamble. Ranking, and some of these are quotes from a while ago, is just in the news all over the place. You have these 10 best and worst pronouncements, whether it be healthcare providers, schools, the hot geographic areas where disease is high, so on and so forth. And in a lot of cases, either rewards and penalties are being imposed, or follow-up in the lab is being done that might be expensive for the highest ranking SNPs or genes or whatever it might be. Or quite frankly, there are situations with schools that may be reputational, not so much financial in the direct sense. So doing it poorly can have very big consequences, and actually doing it well is in general very difficult, not in the sense of producing the estimates, but in having things that are actually stable and quite believable. So the theme of this is to do it well, and also to couple the doing it well with appropriate measures of uncertainty. I guess that means I'm a statistician. These league tables, these are from 2003, but England had been doing a lot of these value-added modeling things. I did a bit of that at RAND, where you measure how much knowledge you inject into these students every year, and then you give credit to teachers in schools or discredit to teachers in school. It's a ranking exercise eventually. Letterman's top 10 list, I'm just trying to make this a little bit fun. New York Times several years ago had a headline, New York's most deadly cardiac surgeons. And some of the ones with point estimates that were up there looking deadly might have been true, but they were based on very few cases. And so it might have just been random variation. In fact, regression to the mean solved their reputation the next year, and that they came back down. But a lot of places where there's this ranking implicit. I decided to be modest and not update it, but apparently, well, actually a week ago we found out it's also still true. Well, it was true in 2008, 9, 10, and indeed in 11. There are some places where you don't want uncertainty estimates at all. You just want to be able to say, hey, Hopkins is ranked by US and World Report as the best school of public health. We might want to decide how they do the ranking and so on, but in this case, I think we just want to leave it alone and say that it's a very valid statement. I'm going to leave out a few of this stuff and just move to a motivating application, but you could translate this to the gene environment or any other situations. But the application I'll use for at least one theme is this thing that goes on every year with the renal dialysis program, and that is to keep score on dialysis centers in terms of lots of things, but in this case, standardized mortality ratios, which are the ratio of observed deaths over expected deaths. And I put those two things in red both to highlight that they're the ratio, but also I'm going to grant that the expecteds are computed well, and the expecteds are done by generally a very complicated case mix adjustment. And so it's actually the case that if you do that poorly, anything I'm going to talk about is almost second order compared to having done the balancing of the books correctly. But for today, we're going to set that aside as being almost too interesting. And the observes I put in red because, at least in this application and many others, ascribing a death in this case to a certain center is not automatic. People get transferred to transplant, so on and so forth. CMS has lots of rules on how to ascribe events to different centers. Again, we're brushing all of that aside, or at least setting it aside, to focus on the more statistical issue. The main issue in terms of doing a good job on ordering these things is that the expecteds are quite variable. I don't mean that they have a statistical variation, but that they vary from center to center. So you've got some precise estimates, some not so precise, and the challenge is, how do you broker the signal and noise appropriately? Well, ranking is easy. I mean, we've all done it, and I'm going to do it in the next slide with 3 numbers, so it's not even a heavy computational load. With those SMRs, to start with, you can take the point estimates, and there are 3,459, I think it is. Here I've just taken the point estimates and ranked every 45th of them, I think. There are not 3,000 or so dots on there. Ranking's easy. There are the maximum likelihood estimates, and what I mean by that in this case is just these O's over E's. And so there they are. It's very easy, and this is just the small version of it, and that is you get these numbers and you rank them like that, with smallest being the 1 and so on and so forth. If you want to convert to percentiles, which I do frequently just to get away from whether the total number of units is 60 or 93 or so on, you know, by certain percentiling rules you get this. So it's easy, you just do it. But the issues are that you're not really ranking the true SMRs, you're ranking their estimates. And so it might be better to try to put this in a framework where you say, I'd love to rank the true SMRs, I don't have them, I have a noisy estimate of them, and so maybe if I embed this in a hierarchical model where I let the statistical procedure give me a posterior distribution on the truth and then use that somehow to be the best ranking, that I'll do better, and that's the theme here. Ranking is difficult because you actually need to trade off signal and noise if you have differential variability. So here's that same plot of 2 slides ago, but now I've put on it the exact Poisson confidence limits, not large sample. So you can see there are several centers here, and again, it's just every 45th in the order, that had no deaths. Some of them are more stable zeros than others. They have a bigger denominator, but compared to just looking at the dots, all of a sudden you realize, you know, maybe this isn't as simple as I thought it was. A lot of these zeros might actually be way over here. Some of these might be here, some back here. It's very hard for me to know by hand how to do this trade-off between signal and noise, and that's why the formalism, at least from my point of view, helps a great deal. So the ranking challenge is a little bit like the Goldilocks challenge, and that is, if you do what has been done in the past, and I think it's not really being done so much anymore because a lot of people, myself included, but many others, are showing why you need to do something better. If you just rank maximum likelihood estimates or other things you would call the estimate, it's intuitively clear that the highly variable ones will tend to be on the edges and the less variable ones in the center, even if in fact all of these clinics are operating in about the same way. And you get the opposite thing with what was traditionally done, and you could say that is completely still done almost always for SNPs and genes and so on, and that is, if instead you test the hypothesis of this unit being just like all the others, and then rank those z-scores or p-values, you get just the opposite. You get the stable ones out on the edges, and the less stable ones inside, because the power is higher for the more stable ones. So you need to somehow have a trade-off routine that is at least principled in the sense that you can discuss what you're doing. And then I think the big however is, even if you do that well, you'll see as I go along that uncertainty dominates this stuff, and you want to make sure to communicate that and use it as part of what you do. So this is just a quick example that maybe you don't need, but at least emphasizes in this application this too hot, too cold kind of thing. So this is a table, I probably could have made it a graph, but I didn't, ranking the MLEs. And the rows have to do with the size of the provider, which links up very closely with with the expecteds and with the stability of the estimate. And So we're counting now how many are in the lower 25% of these, middle 50, upper 25%. So if I did the margin down here, it would be 25%, 50%, 75%. And as you can see, the highly variable ones tend to be on the edge. The lowly variable ones, if I may use that, tend to be in the center. And yes, there may be some truth to that, in that maybe there are some that are actually high and low. But if you go to the next table that's just the same, except now I'm doing it with the z-score approach. Same clinics are in these rows, but now you get just the opposite, that the highly variable ones, the small sample size ones, tend to not ring the bell, and the larger sample size ones tend to. So the Bayesian structuring of this, as you'll see, and that's different from Bayesian philosophy, and we can talk at lunch, or you've all had your lunch, about whether I'm a philosophical Bayesian or just a practical Bayesian. And I suppose the answer is a little bit of yes for the first and a lot of yes for the second, is to develop a hierarchical model or a multi-level model. Once you've done that, use the rules of probability to do the computations you need to do. It takes a little of this CPU, a lot of that CPU, but we've got that one these days, and I'm losing this one fast, but at least I still have a bit of it. Why do I always like to put frowny faces and smiley faces on things that are difficult. The frown is it's difficult, and the smile is it's job security, so that it's nice to have things that are still difficult conceptually and computationally to keep us going. Okay, let's get a little bit formal, but almost no more formal than this. The basic hierarchical model I'm going to deal with, and you can generalize this to have all sorts of fancy things, is that the true underlying SMRs, or log SMRs, or gene expression, or whatever it might be, are unique, but are connected in the sense that they come from some prior distribution. That prior distribution is specified by a parameter or parameters eta, and you can think of this as allowing for it to be a Gaussian prior or a completely non-parametric prior where eta just says it's something. Conditional on in this case, the log SMR for a given unit, what you get to see are the deaths. And they will follow some sampling distribution, this piece being very exactly the same as a frequentist would do. In our case, it's going to be Poisson, but it's whatever it is. And if we're being Bayesian about the whole thing, we'll put another structure on here to say we don't know eta, and that's uncertain. But the guts of what I want to do today is this two-stage model, where we're going to use the y's to inform us on the posterior distribution of the thetas, and then do something with it. So I'm not giving a lecture on computing, but the core of a WinBugs program or a bugs program to do everything I'm doing today are these whatever number of lines there are with the input and output, and maybe we can come back. But the point I want to make by this is not so much teaching about WinBugs programming or Monte Carlo programming, it's just to say this CPU does a lot of hard work once we've done a reasonably straightforward specification of the model. So going back to that picture for a minute, here is the point estimates ordered with their exact confidence intervals. And this is the kind of picture that comes up when you're doing something that's empirical Bayesian or Bayesian, and even if you don't ever want to be such a beast, if you kind of like these pictures, it's not bad. So what does this picture have? The center line here are these MLEs, just like the dots in the other thing. The whiskers are now a standard error of that estimate, and you'll notice I've avoided doing it here, or if you'd like, I'm doing the naive one of just 0, because I don't know how to draw standard errors for things that are 0 anyway. But the idea here is that, if you remember, some of these were more stable than the others in the exact confidence interval thing. The Bayes posterior mean, or the posterior mean, shrinks things towards some common value, and for SMRs, the common value is automatically forced to be 1, or at least close to it. And you get the thing that happens in Bayesian procedures in general, and it says, if you have a highly stable or a relatively stable estimate, leave it alone. Doesn't need any help. But if you have highly variable ones, like this whisker out here, it's almost purely variance, and shrink it back towards the common value. And you can think of this as nothing more than another way of trading off variance and bias to get good mean squared error on estimates. It's really no different nature from deciding whether or not to put another regressor in. So you can kind of make this aphilosophic, and you can also say there are lots of mathematical theorems, lots of simulations, and lots of real-life examples to show that these estimates are just a lot better at almost any purpose you can think of. But they also show something else, and that is if you're ranking, these lines cross. And so the order here is very different from the order here, and if you were choosing between them, well, let's put it this way, there's something to choose between them. Which to choose if you were forced to? Well, if I were forced to, I'd do this, but I'd rather go back and say, I'm trying to rank. I'm not necessarily trying to estimate the log SMRs. So why don't I actually take the ranking goal right from the beginning and see where it leads you? So those posterior means are more condensed, and here's that same plot as I had with the exact confidence intervals, but now I've just done it with the dots are the posterior means and the bars are the Bayes posterior intervals. And you may say, well, Tom is a lousy plotter. I actually don't know what happened, why this migrated up here, but why doesn't he use the whole scale? Because what I wanted to do is use the original scale that I had before and show how shrunken things are. But then I'll be a better plotter guy and do it this way. So one thing you notice, and it's the reason that posterior means don't work poorly at least, is that the posterior uncertainty of these things used to be very, very different for these units. One of the things that the Bayes posterior does, just as a consequence, is try to flatten that uncertainty. And so we're now in a situation where the uncertainty is very similar, and actually ranking these isn't so bad. It's not perfect, but it's an interesting phenomenon of Bayesian things that it stabilizes the uncertain ones, it doesn't do so much for the others, and it kind of balances the books amongst things. Well, here's to me the beauty of the hierarchical and the Bayesian structuring is, if I want to go after especially a non-standard goal, in this case like ranking, I can do the following thought process. I can say, what if I actually knew these SMRs or these log SMRs, and I wanted to rank them? Nobody can force me to want to, but let's say I wanted to rank them. What does that mean? Well, your collaborator may not be able to write this down, but hopefully you can, that it means I'm going to sum up the indicator functions about theta 1 being greater than theta 2 and so on and so forth. And if I put the or equals part in here, then the smallest theta is going to be greater than or equal to itself, and we'll get rank 1, and the others will get what they get. So my goal isn't to estimate the thetas, for this goal at least, it's to estimate R of theta. It's a very nonlinear function, it's a step function kind of thing. But in principle, if I have the posterior distribution for all of these thetas, I also have the posterior distribution for all of these, and I can have the goal of do something good with it. And so I'm giving the kind of easiest example here is, let's go for what's squared error loss, not of the thetas, but of the ranks. And as with everything else in life, squared error is optimized by expectations. So what I really want to do is compute the posterior expected rank. And that's just summing up not the indicator functions anymore, but the posterior probability of thetas exceeding each other. A very different computation from producing the posterior means of the thetas and ranking those. It's really doing all of this in the ranking land. These numbers can then be made in this to be percentiles just so it sits in 0, 1 by this kind of a computation. And you'll quite dramatically, these numbers are not, if you had 100 units, these are not ranging from 1 to 100 like the ranks really would. They're also shrunken. They may start at 15 and only go to 83, and the jumps might be like 15 and 15.02 or something like that. A strong message that we don't have a lot of information there. If you really want ranks, you can force the ranking as these, and so instead of R bar, I call these R hat, which is simply saying rank what you got there and you can show that's optimal. It hides completely the fact that these R bars may be very close, these P bars are very close. It just says go 1, 2, 3, 4, 5 because I want it. But the main point is I've now directly addressed the ranking goal, and we'll get to another mode of addressing it too, but the technology has allowed me to first of all say the hard question. What would I really want to do if I had these thetas in my hand without any uncertainty at all? frequently that's the hardest question for anybody to answer in an applied problem. But here, if I say we're going to rank, we can write that out mathematically, and at least all we need is the laws of probability to tell us what to do. And sometimes it's hard work to do it, but you know what you want to do. Okay, so a little simulation result that I'll spend a little bit of time on trying to explain. It's performance of this ranking procedure for squared error loss of the ranks. In other words, how close are you on average? You may or may not think that's the greatest criterion, but just to give you a feel for what's going on. And I'm doing it with 3 scenarios. One is, this is the ratio of the largest variance to the smallest variance, all of this being where the thetas are normal. If all the sampling variances are the same, then all procedures produce the same ranks. You can rank the MLEs and you'll get the same answer as ranking the posterior means, and you'll get the same ranking as doing the thing I just did on the previous page. And so if you look at the simulated typical squared error loss, when all the units are both symmetric and equally variable, it doesn't matter what you do. And what are the things I'm doing? I'm doing these optimal percentiles. I'm doing the posterior mean of the log SMRs. This is, don't even worry about the formula, but it's the posterior mean of the SMR itself. It's really just an expectation of a log normal. But theta is the log of this, but you can see that you get the slightly different formula. And this is just ranking the MLEs themselves as opposed to the posterior means or the optimal thing. They all give 516. And it's worth kind of knowing that this is better than knowing nothing, and it has to do with how much information is in the system. Let's just jump to the case where the largest variance is 100 times the smallest one, and the progression here is that you have variances that go in a log equal or a geometric series from smallest to largest. So this is like highly variable variances. And you pay a little penalty in the sense that for units that have differential variance, you can't do quite as well as you do when they're all completely comparable. So here's the optimal performance under squared error loss. Posterior means of the thetas still aren't bad because they're balancing the books on those variances pretty well. So one would never care about this difference really. But now if you instead had taken the SMRs themselves as your object of interest and done posterior means of those, you get notably degraded performance, where we all know that if we're ranking, it shouldn't matter whether we're ranking the SMRs or the log SMRs or any other monotone transform. The ranks are the ranks are the ranks are the ranks. So you really want something that, if nothing else, doesn't get affected by the monotone transform. If you go to just using the Y's, which is really the MLEs that are these noisy objects, you pay a big penalty. So this example, it's one of many, but it really shows that once you get to the point of the variability of the units being different, and this is a general statement, but here it's done just for the Gaussian distribution, it's really important to go after the right trade-off, basically. And so you're paying a big penalty by certainly ranking these. A small one here, but if you weren't smart enough to know that you should transform to get things to be reasonably Gaussian, you might be doing this one, and there's a fairly big penalty there. And of course, I could come up with 8 million scenarios that produce things. Now, just so I can tell you, this GMV is 1. This is a hierarchical model where the prior variance for the thetas is 1. And here's a case where the typical sample variance is 1. So that in the Gaussian world, you're doing a 1/2 weighting of prior and sample. That's what this geometric mean of the variances is. And for all of these cases, even the 100 case, the geometric mean of the variances is still 1, so the typical variance is still 1, but they're spread out. If I made the geometric variance here really small, I'm getting more Y's are almost like the thetas. I'll get much better performance, much smaller numbers here. But this is just one example. Taking those same things and looking at what you might call a traditional display of uncertainty, there are 4 panels here where the vertical plot is exactly the same in all of them. It's the optimal posterior mean of the percentiles. And it's hard to see here, but it's the p-bar, so it's the ones that don't necessarily fill out the full range. And the 4 different x-axes, or whatever you want to call them, are, here's the optimal one in the sense of discrete rank. So these are just produced by ranking these. It's not a big surprise that things are monotone. They have to be. This is the one I've got to make sure to remind myself. This is the posterior mean of the SMRs. This one are the Ys, or the MLEs, and this one are the Zs, which are the hypothesis testing. And the more you see non-monotonicity here, the more you know that these are degraded performance compared to the one that should be used. I think the main message here, though, is not so much the jumping around of these dots, but the main message is that whatever these ranks are, they sit in a sea of uncertainty. That these are confidence intervals for the, let's go to the one that's easy to look at. And so, yeah, you might be able to tell that this dialysis center is actually one that is way down here, but pretty much the main message is we don't know anything, even for the optimal one. And so this picture of uncertainty, I think, is as important as anything here. One more example, which I can promise you I didn't search for to make this happen when you see what I mean by the this, but it's an impressive this. This is another example where the analysis is dealing with length of stay. It's again a health services example. For many hospitals, there's so much data that the MLEs are actually so accurate that in fact there's no Bayes action and everything is fine. But just to show a pedagogic thing, we'll take a 10% sample that makes things have enough action to them. So it's a bit of a cheat. This is a case where there's actually a regression structure in the prior with 2 covariates being adjusted for, and so what we're looking for is it's like an SMR in that it's the residual after having adjusted for the reason for stay and the comorbidity status. And it's another one with incredibly discrepant standard errors or variances. And that's true even if we did the full sample, you still get these kinds of ratios. So the least squares mean adjusted population typical length of stay is 14.5 days. And the estimated variability of that length of stay in the sense of what is unaccounted for by these covariates, but is true variation in hospital to hospital truth, is that there's about a 3.1 standard deviation, so that you could imagine that for the hospitals in this framework, plus or minus 6.2 days would not be unusual even after having adjusted for this, and not because of sampling variance, just it's unexplained. The usual, if you'd like, random effects model. So you can think of this as the prior, and you can think of this, prior mean, and this is the prior standard deviation, because it is. So here's another one of these caterpillar plots of the ranks and their spread. This is an example just to show again that optimal is not only better, but is in some cases a lot better. This is the difference of the posterior mean from the optimal ranks, and then the triangles being the Ys, or the direct estimates. The X's are almost hidden in there because in this case things are quite Gaussian. Posterior means do very well. As you can see, the deltas are all over the place, showing that if you believe that what I've given you is optimal for at least squared error loss, you're getting a lot of discrepancy for the triangles. More importantly, and this is where you could accuse me of cheating, I have never run a simulation of a uniform zero correlation distribution on the interval 0, 1 with a random number generator that's been validated that has ever looked this good. I mean, this is almost like put me in jail for cheating, but this is the ranks based on the MLEs, least squares means really, versus ranks based on the z-score testing. And if you ever wanted to see a plot that says these two have nothing at all to do with each other, you probably couldn't do better than this. So it's trying to, I didn't try to make this happen, but it's sending the message that that choices matter in this case. And that in fact, the two extremes of use the MLEs and use the test, you really just, somehow this data set has conspired to give you incredible differences in this whole thing. I'm leaving these out, fortunately, because they're small. And go on to another, not another Bayesian formulation of the hierarchical model, but another goal that you might have in your analysis. And this is one that's a little more relevant, I think, not only for the health services application where CMS penalizes the poorly performing units, but for gene identification, SNP identification, and other things where you actually say, I don't really care so much how the ranks go for the things that are down there at low and in the middle, if high is the thing of interest. I'd like to do a really good job of selecting the top 1% of SNPs or 5% or 100 SNPs or whatever. And so take a different criterion, one that is not squared error loss, but says I'm going to keep score by counting up the number of or the probability that the true percentile for this SNP or this unit is below some threshold gamma when I estimate it to be above gamma. And this is indeed a Bayesian FDR. And I'm going to add to it, and I'll tell you why in a second, the other side, which is the probability that you went the other way, that the truth is above and the estimate is below. Because everybody's got to be someplace. There's a good joke about that, but I won't give it. Any misclassification above has to be coupled with a misclassification below because there are only a certain number of places to be. So the sum of this is actually like the FDR divided by this threshold gamma. And I like this normalization because it actually flattens the dependency on gamma, which we'll see in a few minutes. But if you wanted to, this has dividing by gamma has nothing at all to do with what you're going to use as your optimal estimate. It's just deciding where to keep score. So if the data were completely uninformative, in other words, the sampling variance were infinity for everything, this operating characteristic would give you a value of 1 always, no matter what gamma is. That's kind of the normalization. And of course, if they're fully informative, it would give value 0. So the idea here is going to be to come up with the P super est, or the pests that minimize this function. And it doesn't take much to see that the way you'll do it is to order these things in terms of their posterior probability of exceeding gamma. And that will be the optimal way to minimize this. So before I do the optimal thing, what I've done here is to take that computation of the posterior probability of exceeding a threshold, and in this case it's exceeding, either the upper or lower 25%. You would never want to do that for genes, but just to make it easier to see what's going on here. This is the collection of posterior probabilities of being in the top 25% of the dialysis providers. That's a bad place to be because it's SMRs. Similarly over here to be in the bottom. I'm ordering though now here by these P hats. They were not designed to optimize this criterion. They were generalized squared error loss. And that's why you get, these have all 3,459 on them. That's why you get these fat lines, because this ordering is not exactly monotone with these probabilities. We'll get to a plot in a minute that's much more boring in that it only has a line because you just do the right ordering. But this is to show that general purpose ones don't do too badly on this, but to show some other things. If there were no information in the data, then both of these curves would be flatlining at this green thing. It would just be, well, the probability is 25% because it's 25% up there. If you had fully informative information, being careful of what R does, it would be flatlining to there and jump up immediately to 1. The operating characteristic curve would say, no chance, no chance, no chance, bang. This one, these are in between, so it says there's some signal, but the main message here again is uncertainty. In that for the dialysis centers that are pretty much on the threshold of this upper 25%, that lowest one only has about a 40% chance of really being in the upper 25%. And you have to get way up here to the ranks that are up there, or the percentiles up there above 95 and so on, before you even get a 90% chance of truly being the ones that are up there. So this is another kind of uncertainty plot. If you do it with the, I'm going to quickly go to the plot and then I'll go back if I can find the plot. If you do the optimal ordering for this goal as opposed to the other goal, you're going to get thin lines because, in fact, these are now completely lined up. They're ordered by these. And for the moment, all I want you to do is doesn't matter which curve you look at, but you get the same kind of operating characteristic curve that if it were a perfect classifier would be 0 here and jump up to 1. If there are no information at all, in this case I'm doing top 80%, it would flatline at 0.2. So you can see there's some information, and we'll come back to these plots in a minute. Should have thrown one in there earlier, but I didn't. This is a easy computation to show that what you want to do is order the clinics or the units, whatever they may be, based on these posterior probabilities of exceeding this gamma thing. Early on in our research, we realized that, or at least we didn't realize, what we did was a naive computation of this, of running MCMC essentially forever, to get a good estimate of the posterior distribution of each of these clinics in this case, and then doing these computations. And it was endless because you have to, we had 3,459 of them. To get a fine-grained estimate of their probabilities, you need thousands and thousands and thousands of draws. Rongheng Lin, a graduate student of mine a few years ago, we came up with a nice theorem that says you don't actually have to do that. All you have to do is produce the pooled estimate of the distribution of all of these SMRs, or log SMRs, or whatever else you want it to be, by simply, in the MCMC world, taking all the draws you have from all of the clinics, throw them in one big hopper, order them, and let that be an overall pooled distribution that I'm calling G bar. If you're in a more mathematical statistics world where you don't have to do MCMC, you're just taking all of these posterior distributions and averaging them. And that a very trivial computation says you get exactly the same ranks, and there's a theorem that floats around here to say, if you want to find the probability of exceeding gamma up here, just find the gammath percentile of this pooled distribution, and this pooled distribution is for free, if you'd like, once you've either done the math or the MCMC. The threshold you should use here is just that percentile, and then just go take its single posterior distribution and compute this probability and order on that. And you get exactly the same answer. So this has a dramatic computational advantage, but it has an advantage even if it's not computational. This percentile is back in SMR land, or log SMR land, or whatever context you're in. So you actually get a number here that relates to the context and isn't just a rank or a percentile. So it helps map things in. This computation, not this computation, but this criterion is very similar to one that Sharon Lees Normand has used in health services work of probability of exceeding a threshold. And our only innovation, if you'd like, is to relate that threshold to a percentile of the rank distribution. So everything I showed you with those pictures was based on a Gaussian distribution for the log SMR. But the nice thing is, and one of these things that has really allowed Bayesian formalism to be quite objective for problems where you have a large number of units, is that you can become very much more empirical about the prior and not necessarily have to say it's Gaussian or it's anything. So this plot is saying, we've done the Gaussian things in two different ways, but eventually this dotted curve is saying, here's our best estimate of the prior distribution for those dialysis centers with a mean and a variance, and this is actually for the log SMR. But we also ran a smoothed non-parametric approach to it, saying all we're admitting to is that there is a prior, not in any way saying what it is, not giving it a name, and smoothing it. And you end up with this solid curve, and you could argue about whether we should smooth it a little bit more. The point is, the fact that it looks reasonably Gaussian in the center has nothing to do with our having made that assumption at all. It just happens to be that way. But we do end up with this little blip out here of a log SMR of about 0.5. Interestingly, these turn out to be the for-profit dialysis centers. I mean, not completely, but most of that little subpopulation is populated that way. The point being, everybody's subjective to some degree on deciding on the sampling distribution. Is it Poisson, is it negative binomial, or whatever? Frequentist Bayesians, we all have that. With these large data sets, large in the sense of number of units, so we get lots of draws from the presumed prior, we have the luxury of saying the only assumption we're going to make essentially is that there is a prior. And then let the data give virtually all details on it, and then use this shape, the solid curve shape, in our inferences and get a much more robust approach to things. I'm going to do just a couple of more things. I don't want you to look at necessarily to look, well, I don't want you to try to look at the details of this, but to say another nice advantage of the Bayesian formalism that allows you to do things that are at least more difficult to do as a frequentist is to say, I've got these true thetas, but I actually, in this case, we have 4 years of data. So we have the true SMRs or log SMRs for 1998, 1999, so on and so forth. Maybe we should build a model that includes both this cross-sectional combining that I've just done, but also the idea that the true SMR for a given unit for next year isn't a complete random draw from what it used to be, but is, in this case, an autoregressive model. So don't bother looking at the details, except for me to say, this stuff says, let's build an autoregressive model longitudinally for these thetas, and still this general shrinkage model cross-sectionally for these thetas. Write the model in terms of the thetas, which we never get to see. We get to see the y's, and then let the technology take over to do what it needs to do things at the theta land when we only have the y world, and let the computer work hard to do that once you've formulated it. So that's what this plot is showing. It's saying if you take and do literally pooling over years, you get that solid curve. But that's not paying so much attention to the fact that the years might actually be different. These curves, which superimpose quite a bit, are looking at what happens when you take things year by year, and it doesn't look too bad. You can see, first of all, that the year by year stuff actually looks like the years are quite similar, and that if you literally pool, meaning you're getting a lot more sampling precision or lower variance, that your operating characteristic curve is lower down here and higher up here. In other words, better. But if you do this partial pooling, so to speak, and now I'll just focus on one of the years, 1999, 1998. You could do this for any of the single years. But let's say, in one case, let's just let that year stand on its own. The autocorrelation of the underlying thetas is 0. You get this dotted curve, which is exactly the one we had up a while ago for the 1998. If you build the autoregressive model for all 4 years, but now I'll just look at how these other years help this year, it turns out that that autocorrelation is 0.9 on a 1 year to 1 year basis. You get some help still. It's helping, and it's actually helping almost as much as pooling, just because the 0.9 is very close to 1. But you build a model that says we're not going to pool things, but we'll let the data tell us how similar the longitudinal stuff is for each clinic compared to a total independence model, and have a fancier model for stabilizing a bit over time as well as over space, if you want to think of that. And so how do we get this estimate? It comes out of the Bayesian Monte Carlo that says we want to get a posterior not only for these thetas, but for the correlation parameter, and you let it rip. So you get, this is one of the last slides that I'll do. If you look at, you can look at more years, but if you look at 4 and you measure how much longitudinal variation there are in these ranks or these percentiles. So this is squaring around the typical percentile for a given clinic over the 4 years, going from 0 to 3, sum it out over all clinics, multiply, take the average and multiply 100 so that you get a number that's easier to tabulate. And look at that when you let every clinic stand on its own. So that's this number in units that may or may not mean anything. These are these operating characteristic numbers, the correct classification numbers with a threshold of 0.8 if you just let every year stand on its own. And then over on the right-hand side is the one that includes the autoregression, where the estimated autoregressive parameter is 0.9 with lower Bayesian prediction interval of 0.88 and 0.92 is the upper. That's what this notation means. It's the confidence interval, basically. You see that you not only get a dramatic reduction in the longitudinal variability, which may or may not be good, but at least it says things are not changing so much over the time as if you just did slice by slice by slice. And you get a quite notable improvement from, say, roughly 60 or 61 to around 50 for this, essentially this FDR kind of performance probability by allowing the data to combine. And quite frankly, if things did not look correlated over time, this 90 would probably be down at 20 or so. So you're letting the data do it still. Your opinion is that you're going to allow it to happen. I think with the time remaining, I'm going to just stop here by saying it's one of many examples where I think a structured approach is needed. You don't need the word Bayes there to make it a structured approach. That make it a structured approach where you clearly keep your eye on the goal and then let the technology take over to give you a good performance for that goal. And in a lot of these situations, I don't know how to formulate it without doing it in this hierarchical approach where you know what you might do if you had the things before you but you don't, and you want to use the hierarchy to help you get a window on that, and then the laws of probability to do the complicated sorting out, if you'd like. The uncertainty dominates, whether it be that first plot of the confidence intervals or these operating characteristic plots. They aren't fabulously near zero and jumping up to be near one. That brings up one of my favorite expressions, is that we're doing optimal things, but the best of a breed can still be a dog. I mean, you still have an obligation to evaluate the performance of the thing you did, even if you know it's best. And estimates should always be accompanied by uncertainty assessments. And I'll say a little bit more, and I'll just page back here and close with a slightly of a more policy statement or process statement. If your goal is to identify, and I'm making these easier to look at by making it, in this case, top 20% or bottom 80% instead of getting it right up here near the edge. Let's say that you are the Center for Medicaid and Medicaid Services, and you're really using this to do financial penalties, or if you're down in this range, doing financial rewards. I quite frankly think that if you have some nominal 100% penalty, you should actually attenuate that by multiplying by these probabilities. And that not just to put up this picture of the uncertainty, but actually have that uncertainty influence the policy decision, in this case, how much money, quite frankly, is being charged. And if these posterior probabilities are much lower, you shouldn't really be penalized people more than you might penalize the people down here. In a gene expression or identification experiment, these kinds of probabilities can give caution to going too far with all of these instead of maybe a few of these, and to let some science take over in deciding around the boundary that the message is, this is our best bet, no question about it, but beware, the bet's not very good, and you might want to be careful and not do more than a few of these, or look for previous history or pathway issues and so on that might help you decide on, just like NIH does when it's doing its grant awarding, to reorder the order to address institutional priorities. Well, in this case, to address genomic priorities or something. So I'm going to stop there, and as you can see, I'm stopping right at the and, because I don't think there's time for the and we'll just leave it there.